This is This Week in Science and Education, Episode 32, recorded Tuesday, March 29th, 2011. Neutrino detectors in Antarctica. This is This Week in Science and Education, the show that talks about all things science and health research related and how to take these latest discoveries and bring them into the classroom. On today's show, neutrino detection in Antarctica. Ice cubes. What does it all mean? Coming up next on This Week in Science and Education. This Week in Science and Education is brought to you by Sheridan Institute of Technology and Advanced Learning. At Sheridan, students shine brighter. Visit SheridanShineBrighter.com. Hey everybody, it's time for This Week in Science and Education. This is your host, Kevin Cougler. Interesting show today. We're going to learn all about the Ice Cube Project. What is that all about down in Antarctica? Well, to tell us all about it, we have Mike and Mark from the University of Wisconsin today. But before we get to them, let me introduce my co-hosts. One of them you'll be familiar with, and one of them maybe not so much, but you'll be getting more familiar with them. Hey, Colin Jagoe, Kawartha Pine Ridge District School Board. How are you today?
Hi, everybody. I'm great. Glad that we can get a chance to talk to people here finally.
Yeah, this is great. We don't go outside of the country very often, so it's kind of interesting that we have a chance to do that today. I'm really looking forward to talking to these guys.
It's a very cool project too.
We should point out that Dr. Thomas Merritt, who would normally be with us, has been called away on, should we say on VROC special assignment? That sounds really important.
Sure. Yeah, let's do that.
Okay, he's been called away on special assignment. We hope to get him back in a couple weeks, but he will be taking a little bit of a hiatus. And our good friend Dr. Brent Sinclair from the University of Western Ontario was kind enough to pinch hit for him. Hey Brent, thanks for coming on the show.
Hey, not a problem. I was thinking about Antarctica this morning actually because I was cleaning out a freezer.
Well, we appreciate you coming on, and you have some big shoes to fill, aren't you? Thomas, he comes up with a lot of interesting questions, so you've got the pressure on you today, but knowing you, Brent, I have a feeling you're up to the task, so thanks very much for coming. Mike and Mark from the University of Wisconsin, good afternoon, fellas. Actually, maybe it's not afternoon. What's the time zone in Wisconsin? You a couple hours behind us here, or?
We're on Central Time, just 1 hour off from you folks.
Okay, so it is the afternoon. Well, we appreciate you guys coming on the show today, and we had a couple technical challenges, but we're working through them, and so we're pleased that we could have you on. Maybe we could start by just having you talk to us a little bit about who you are, what the nature of your research is, and from there we'll delve into the project. Take it away, Wisconsin.
Hi, my name is Mark Krasberg, and I'm a researcher here at the University of Wisconsin. I joined the Ice Cube project around 7 years ago, and I've had the privilege of being able to go to the South Pole during the austral summer, which is our winter, for about a month and a half every year for the last 7 years as we built the project, as we built the telescope.
And I'm Mike DuVernois. I actually just joined Ice Cube about a year ago. I'd previously worked on some other neutrino experiments based on high-altitude balloons, and had been down to Antarctica for that a couple of times, and then spent about a month and a half there this past season at South Pole.
Well, I'd like to talk a little bit about what your experiences have been down in Antarctica and at the South Pole, but why don't you start by telling us a little bit about Project Ice Cube? What does that mean?
So Ice Cube is it's a neutrino telescope. We're building it deep in the ice at the South Pole. The South Pole is it's about 2 miles thick of ice. We need a clear medium for this telescope to work, and so we actually drill 1.5 miles down into the ice and deploy light sensors in a huge three-dimensional grid that's a cubic kilometer in size. And that forms a weird type of telescope. And the purpose of the telescope is to detect neutrinos, which are particles that are incredibly hard to detect. And one reason why we're building such an enormous, we're instrumenting such an enormous volume is because when you're trying to detect something that's incredibly hard to detect, often you need to build something really big.
And it really is a telescope, though. The objective is to look at astrophysical sources of these neutrinos. These neutrinos are able to come across through the Earth, but also from vast distances in the universe, and out of the sources, coming deep out of the sources of the neutrinos. And the neutrinos would track very high energy phenomena in the universe. So this really is a telescope in that sense. And we like to think of it as sort of a new view on the universe, a new window. You know, when radio astronomy, you looked at the sky in the radio, there were new discoveries. You looked at the sky in X-rays, new discoveries. And here we have an entirely new particle to look at the universe.
And why the South Pole? Why aren't we building the telescope in the middle of New York City? The answer might seem obvious, but why are we building it down in Antarctica?
So we're putting 5,000 light sensors in the ice, and these cosmic particles that we're looking for give off faint traces of light. And so what we have to do is, in order to see that light, you have to instrument a clear medium, and you have two choices. You can either build this thing in, like the ocean, deep down. It has to be dark, so you have to go way down where there's no light. So you can't just, build it in your backyard. You go deep down in the ocean, or you go deep down underground in the ice. And it turns out the ice underneath the South Pole is incredibly clear. It's clearer than you could make it in a lab. We have tiny little LED light emitting diodes on our modules that we can use for calibration. And the light that when we flash these things, the light travels 2,000 feet, 600 meters through the ice.
Wow.
And light sensors 600 meters away see this little flash of light from really far away. The light is incredibly clear.
And there were efforts to build such experiments in the ocean, actually. And my first introduction to the ideas about IceCube was a graduate student, and there were sort of two rival projects. And one of them was going to be built at the South Pole, ultimately IceCube, and the other was going to be built off the big island of Hawaii. And it seemed obvious which was going to be easier of these projects to build. But it turned out that the difficulties of building such a large cubic kilometer detector in ocean water are much more severe than basically the logistical problems of building at the South Pole. So down in the deep ocean water, in addition to the creatures, which emit light once you get down pretty deep, there's also radioactive decays, mostly of potassium in the ocean water. So the ice, South Pole ice got started looking better and better, sort of historically in this field. And there are a couple of smaller projects in the Mediterranean in the water, but they have a lot of these same difficulties with backgrounds as well as currents. The water down at the South Pole doesn't flow very quickly, so your modules are pretty stationary and are able to be surveyed.
I was going to go to Brent for the first question, but I think Colin's got his hand up there. Am I reading the body language right?
Is that what I'm doing? I got my hand up. Nice, that's good. Okay, I'll take. We actually had the chance to go to the Sudbury Neutrino Observatory a few months back and learn about what they've done up there and what their plans are in the future. So you talk about the IceCube actually being a telescope, which is fascinating. So the first question I have is there a way within the detector to actually use it to pinpoint sources of things? Because, the telescope looks at specific spots. And I know, depending on sensitivity and resolution and all of that sort of stuff, sometimes with things like radio astronomy, it's sometimes harder to find specific sources. And it seems to me that with neutrinos, it would be even harder. So if you're using it as a telescope, is there a directionality in some way to start to actually find sources of these things as you actually detect them?
Yes, the telescope, these light sensors are in this very, very large, cubic kilometer, three-dimensional grid. And what ends up happening is a neutrino, or it's actually the byproduct of a neutrino hitting a piece of ice or a piece of rock, you end up with a particle typically called a muon, a high-energy muon, and it travels through the ice, giving off this small, faint blue light called Cherenkov radiation.
Cherenkov radiation.
And so this particle is, because it's a high energy telescope, the particle that travels through our telescope that comes from the neutrino actually travels within a degree of the original direction of the neutrino. So this particle that we actually end up detecting is traveling along the same direction as the neutrino with almost the same energy as the neutrino. So the amount of light that this thing gives off is correlated to how energetic the particle is, and it has a direction to it. And the light from this particle goes outwards away from the path, and it hits our light sensors at slightly different times. And the timing on these sensors is accurate to 5 billionths of a second. So what ends up happening is up to several hundreds of these sensors get hit at very slightly different times, and a computer algorithm can then reconstruct the path the particle took as it went through the detector, as it went through the telescope. So then you can trace it back, and you can point back to where the particle came from.
Right.
So you have sort of resolution on the sky on order of a degree or so.
Of a degree, yeah.
And this is really a sort of pioneering effort in looking at the sky in neutrinos. A degree is not does not seem like high resolution to sort of traditional astronomers, but we're looking for the first handfuls of detections, which would probably you saw 10 events across the sky. You end up doing a statistical analysis. What sorts of objects are producing them, and perhaps in a future generation, we'll try imaging down into the source. But it really is a telescope in the imaging sense.
Yeah, and we're looking to find the first source of high energy neutrinos. No one knows where they come from. People are pretty sure that they exist, but nobody knows. There's no known sources.
Now, when you say high energy neutrinos, oh, sorry, Kevin. This
No
one,
problem,
the
Colin,
difference between, is a solar neutrino the same as a high energy neutrino, or are those two different things?
Yeah, we don't. Our telescope can't even see the sun. We're only interested in the most energetic, highest energy stuff in the universe.
The solar neutrinos are much lower energy, and what we do have a local source of is the very, very high energy tail of the atmospheric neutrinos. So the cosmic rays, the charged particle cosmic rays, come in at a wide range of energies, but include very, very high energy particles. And so a cosmic ray impacting anywhere in the atmosphere, creating a shower, can generate these atmospheric neutrinos. And this isn't the main focus of IceCube science, but there are these locally generated high energy neutrinos as well. But we really want to look at ones whose origins were in active galactic nuclei, in pulsar systems, in high energy collisions of galaxies and the like.
Okay.
So just one thing, I think you have something like 10 billion neutrinos going through your thumb every second, and almost all of them come from our sun, and those are low energy neutrinos. And what we're looking for is these high energy neutrinos, hopefully coming from some other part of the universe that no one's ever detected before. No one knows where they come from, and that is just a very small number per year that we would actually detect going through our telescope at the most.
Oh.
It's a very, very small number.
Okay.
Mike, I'm going to ask you to be the designated mute person. So when you guys aren't talking, if you can just click on that mute button there, that would be great. So you're a world-class researcher and the mute guy too, please. Brent, some questions for our guest today, if you will.
Yeah. No, I'm interested in some of the practicalities of this. So I've been to Antarctica 8-9 times, something like that. And I worked north of McMurdo Station up on the coast, working on the little bugs that live under rocks and things like that around the penguin colonies. And I'd always I'd heard about this. So tell me if I've got this straight first of all. So what happens to build this array? You drill a big deep hole, and then you drop a kind of a string down that which has detectors at different points along the string. Is that correct?
Yeah, that's correct. So the drilling is done with hot water, and it's a 20-inch diameter hole that goes down to 2,500 meters down in the ice, and that's within a few hundred meters of the actual bottom of the ice, down closing in on the rock. And then these electronics modules, the optical modules, are on a cable, and the whole system is dipped down into the warm water until it's in its correct place, and then hooked up, and the ice freezes in around it.
Yeah. So when we drill it, I was just going to say, when we drill the hole, it's a hot water drill, and so, as Mike said, you end up with a column of water, and the sensors get dropped down, and then over the course of actually weeks, it can take for that fairly narrow hole to actually freeze back.
Mm-hmm. So do you just have these things deployed around the edge? So you sort of marked out your sort of one by 1 kilometer patch of snow. Are they just around the edge, or are they all through the block of ice, the one cubic kilometer block of ice?
So it really is a 3D grid. The string space or strings going down are spaced by 120.
So the module, vertically the modules are spaced 17 meters.
And then horizontally the strings are spaced by
125 meters
125
from
meters.
one string to the next, and it's in a hexagonal grid. And so we finished building the telescope this year, and we ended up drilling 86 holes. And there's 60 sensors on each hole. So we have something like, including a few modules on the surface, we have something like 5,400 modules that are taking data, that are transmitting information to a central building in the middle of the array at the surface.
How deep is the first sensor? So
it turns out that the ice is not that clear in the first few hundred meters, and we actually it's a cubic kilometer array, but the first sensor is about 1,500 meters down. So we've instrumented a billion tons of ice between 1.5 kilometers down and 2.5 kilometers down over a square kilometer.
Cool.
I just want to point out, sorry, Brent, I just want to show that Colin's got a visual up on screen there. What are we looking at there, Colin?
Yeah, I just pulled this up off the IceCube website, and this is a diagram showing sort of what the thing looks like, and the hexagonal array, and then the depth, and then down below here's where all the sensors are, like you said, over a kilometer down before we start. And then there's a little Eiffel Tower down here for scale too, just to show people what it actually looks like and how big it is. So this gives you sort of a 3D idea of what it looks like.
Super. Thanks for doing that.
We end up drilling something like between six or seven Eiffel Towers down, or maybe it's 8. I forget. It's like long way down.
We're talking today with Mike and Mark from the University of Wisconsin. We're talking with them about the IceCube project down in Antarctica. When we come back, I want to ask some simple questions. Just basically, how do you get to Antarctica, and what's it like to travel there and do research at the South Pole? But before we do, I want to mention our good friends at Mueller Systems here in Woodstock, Ontario. If you have some data or you have some important pictures and documents and that all-important presentation that you need to give tomorrow, and you don't have it backed up across the cloud, you just don't have a 100% efficient backup method. So we would encourage you to check out muellerdata.com/VROC. That's muellerdata.com/VROC. And if you visit that website today, you'll be able to download their software free of charge for 90 days, test out their system, and see if you like it. Does it work for you? Does it help you restore documents easily? We think it does. We use it at VROC, and we've had to restore it before in the past. So we thank Mueller's very much for their support. And with that in mind, back to the show, talking with Mike and Mark from the University of Wisconsin. And it comes to my mind, gentlemen, that, I'm a grade 5 student, and of course our listener base is anywhere from grade 5 up to grade 12, and teachers in the classroom all around the world. And perhaps they don't know what it's like. Just simply, how do you get to Antarctica? What's the, does it take a couple of weeks, couple of days? Can you fly there out of New York City and land in the middle of the ice? How does this all happen, if you wouldn't mind just letting us know?
Well, we start off at the airport and fly to Christchurch in the South Island of New Zealand, and there all the logistics for the U.S. Antarctic program flow through Christchurch. Get down there, and there's a clothing distribution center, and you go get your cold weather gear. When we've done experiments at McMurdo, it's certainly no colder than McMurdo's on the coast of Antarctica. It's no colder than it gets here in Wisconsin or where you folks are. But to go to the South Pole requires a good commitment of heavy gear, and so we check out. We get loaned our gear there, and then from there. We take military transport, U.S. military or New Zealand military transport down to the ice.
Yep. One thing I should point out is that maybe it's I didn't know this when I joined the experiment. You can only fly to the South Pole basically during the summertime, and so at the South Pole during the summertime, which is basically from the beginning of November till the middle of February, it's light 24 hours a day. And the temperature at the South Pole is above minus 50 centigrade. When it gets below minus 50 centigrade, planes stop flying there. So we're limited to doing our work at the South Pole between the beginning of November and the middle of February. And then at the middle of February is when the temperature reaches minus 50 C, and it's called station close. And then between middle of February and the end of October, there's basically no way for anyone to get to the South Pole or to leave. And so there's about 50 people there now who are working there now. 2 of them work on our experiment. They're called winter overs. And they basically are keeping our telescope running during the South Pole winter. So when we go down, like I would never want to stay there for a year, but when we go down, it's light 24 hours a day. It's cold, but it's sunny, and it's really not that bad. During the height of the winter, which is going to be in a couple months, it'll get down to minus 100 Fahrenheit, which is about minus 80 centigrade, and it's just nasty. And then of course it's also dark 24 hours a day at the height of the winter.
Mm-hmm.
Colin, you've got another slide up there. What are we looking at now, Colin?
Well, I was just looking through, like I said, the IceCube website, and I'm guessing this is sort of the landing strip and the little base there that we're looking at. It looks just like looks like an airstrip to me, but just sort of sitting right on the ice with all these little buildings around it, and then it's sort of obviously a shot from the air showing it just sitting literally in the middle of the ice cap in the middle of nowhere. So it's a really, really cool shot. Gives you a good idea of what you're looking at, I think.
Yep,
Sorry, guys, go ahead.
So the runway at the South Pole is a skiway, and the only planes that can land there are landing actually on skis. Mm-hmm. In McMurdo, there are ice runways that are nicely packed for wheeled airplanes to land.
And it's a surprisingly busy runway because that's the only way for supplies to get to the South Pole efficiently. For example, you need something like 200 flights during the summer season of the military planes to come in to drop off fuel that will then last the station for a year. So you can have several flights a day arriving on this landing strip, primarily bringing fuel and supplies that will last the station for the rest of the year.
Mm-hmm.
Brent, what was your experience like traveling down to Antarctica? Did you have a similar experience?
Yeah, so I'm from New Zealand originally, actually, and so we'd drive to Christchurch and then get our gear. Working with the New Zealand program, so it's a much smaller operation, and they piggyback a little bit on the American program. So I would fly down to McMurdo Station, which is the stopping off point for these guys, and then from there we'd jump on a helicopter and fly usually north to areas along the coast. And so I was working on small insects and coastal areas where there's a little bit of ice-free land. So I see this polar plateau thing when we're up high in helicopters and things. I see all this big expanse of ice, but we haven't really had to deal with it very much, other than when pieces of it fall off and float past on the sea. So one of my questions that I had was that, so the South Pole Station is built on a glacier essentially, isn't it? So you've got 2,500 meters of ice underneath it, and there's still occasionally snow falling which builds up. So how do you deal with that when you've got this thing that's frozen into the bottom, and you've got ice building up on top of it? So presumably you have to keep kind of making your cable longer, and presumably it's also moving as well. And if it moves at different depths, like, do you run the risk of the whole thing being distorted or things being broken?
So, the horizontal cables, the cables that would sort of be near the surface, going from these strings to the counting house, to the experiments, central computers, and data acquisition, are all trenched, and so the blowing in, the drifting snow does not affect the cables at the surface. Where this effect definitely occurs is our main building, and there's probably some good photos on the web, is up on stilts. Snow blows in, and you re-raise the building. And so there is slack for all of these cables that are stored up in these underground vaults, basically, big cable vaults, so that we can take out the slack for far more years than the experiment would run.
Yeah, the buildings at the South Pole have a tendency to basically slowly get covered by the drifting snow. And so the first U.S. station that was built in the late 50s is now 30 feet down under the ice. It was abandoned a long time ago, and the station that people live in now to work at the South Pole is actually the third station. The second one was actually decommissioned just a year or two ago, because they've basically been slowly sinking down, or effectively sinking, as the snow is drifted in. And the new base, the new station, has, as Mike said, it has the ability to be raised several times during its lifetime on these massive stilts, so it can stay above the snow. The other question you asked was about the glaciers. The glacier is moving at a rate of about 10 meters per year. So there's a South Pole marker at the actual South Pole, and on January 1st every year there's a ceremony where it's picked up and it's moved to its new location. And so, the station, basically the station, everything in our telescope, everything is moving at something like 10 meters a year sideways, and the South Pole markers will basically move in the other direction, just where it's kept in the same place, and everything else is moving away from the one thing to worry about is as the ice is moving at about 10 meters per year, it's not necessarily moving at 10 meters per year at the surface and at the bottom, right? At the bottom, the ice is kind of stuck to the bedrock, and so, that's called shear, and you can actually have a different rate of drift, a different rate of movement as you go deeper through the ice. And that's something that we're concerned about, because if the modules at the bottom are moving at a different speed than the modules at the top, then eventually between them will break. Now we have these little light LED. I mentioned these before. These light LEDs that we can flash, and that's for calibration purposes. And one of the things we do with that is try and figure out if the modules, where the modules are, and if they're moving relative to one another from year to year. And so far, we see very little movement, very little of this shear between the sensors as you go down through the ice, which is good news for the lifetime of the sensors at the bottom.
Well, I'm back with you, gentlemen. Sorry about that. We lost power here, which actually hasn't happened for a long time, but I don't know if you've watched the news. A couple of days ago, we actually had an apartment building blow up in my hometown here of Woodstock, Ontario. So, the power went out, and immediately I'm thinking, oh my goodness, what's going on again? But it's quite a scary little item in the news. Anyways, I'm back now, so thank you. Brent, any last questions for our guests today? We're a little shy on time, but I want to give you ample opportunity to talk to these gentlemen.
I think I've grilled them probably enough. When do you next head down to the South Pole?
Well, I'm headed back down there late in November this year, working actually on another experiment that has a large overlap with IceCube. It's an experiment called ARA, which is using a radio technique, very, very similar to the Cherenkov light emission, but in the radio frequencies. And we're building out a little bit past IceCube to extend IceCube's reach to even higher energies. So that's I'll be down there for another month or so in December.
Colin, just before we go, maybe you could put a little educational spin on this for us. What does all of this mean for the students in the classroom today?
Well, yeah, it's very interesting. I was sitting here, that was, you know me, Kevin, it's always going to be my final question. I mean, it's obviously physics, but very high energy, obviously high energy, but high-end sort of physics. As a K-12 educator and a high school science teacher, what are some of the things that, you tell high school students and high school teachers about what you do and how it applies to sort of the learning of basic physics? Is there a way of pulling those things together so that when students are learning the basics of Newton's laws and particles and the foundation, that they can see long-term what you guys are doing and how it all ties together?
Well, I have in the U.S. Middle school age daughters who are 11, and their classes were following my work down at the South Pole this past season, and IceCube has brought their high school teachers down for a number of different occasions to make connections back to their own classrooms, and then sharing those experiences out to other classes. And I think the sort of main items that we were able to connect to the teenagers and the children with were sort of the nature of how do you answer a big question. This experiment is hardware, but we need to make that hardware connection over to theory, things in our books. And this is it's an active process, and it's ongoing. It's not history. It's not a historical document. And that these are approachable, normal individuals doing this work, and the whole South Pole, the Antarctica, give sort of a natural entree to that by being interesting. Heavy coats. How cold is it? Did you see penguins? How do you keep your equipment operating? And the like. So that gave sort of the initial interest, and then try to make these connections between big science experiments and sort of the body of knowledge.
Right. Yeah, that's good. I mean, we talk to a lot of people about that, and it always comes down to the doing of science and not necessarily the specific content when you're talking, to teenagers, whoever, about what you're doing. If you can understand kind of the process of how, like you said, you nailed it, how you answer a big question, right? And that's key, and that's a learning that can take you a long way in any science. So that's really cool to hear that you're doing that and taking high school teachers down to sharing that. So that's amazing.
Great discussion here today, gentlemen.
And thank you guys. Thanks to Mike and Mark from Wisconsin. It's been a real pleasure talking to you guys today. We appreciate your time and appreciate you coming in and spending some time with us. So thanks very much.
Yeah, it's been fun. I've enjoyed it.
Excellent.
Excellent. Well, on behalf of the absolute Kevin Cougler and Dr. Brent Sinclair at UWO, this is This Week in Science and Education. So thanks very much for your time. Thanks for watching, everybody.